Okay, welcome back, guys. We're going to be covering section 3.5 today. And as you can see, this is on solving systems of equations. Well, more specifically, systems of linear equations. Okay, so when I say linear equations, that just means that nothing can be squared, nothing can be cubed. Okay, these aren't going to be quadratic or cubic. And, well, let me show you. We're going to see two different types of systems. A system in two variables, okay, so something like this one. Example 1, where we have an x term and we have a y term. Now remember, think back to 2.1. This is just a linear function. You could solve this for y, and you'd have y equals, and then it would be in that form mx plus b. We could do the same thing for this one here as well. But we tend to write these linear equations like this. We try to get all of our x and our y terms on one side and have our constants on the other. The reason is because it makes it easier for us to actually solve them. Okay, so that's when we like to set them up this way. But this would be an example. And what you would be doing to solve a system like this is you'd be trying to figure out a value for x and a value for y that will not just work for one of these equations, but will actually work for two, for both of them. Okay, and so typically there ends up just being one value of x and one value of y. It'll make both of these equations true statements. Okay, so I think in this part 1 video we'll just focus on solving systems of two equations, okay, like this, in two different variables. And then in part 2 we're going to expand, and we're going to solve systems of 3 equations in 3 variables, okay, like this. And I actually put a system of 3 equations and 3 variables right here at the top of your notes. I was looking for a fun video, but I couldn't really find one, so I did find some different websites. And so the question is, well, where might we see these in real life, or what types of scenarios, what are some scenarios in which we could employ the skill of being able to solve a system of linear equations? Okay, and there's lots of things. Okay, cost and revenue problems. We've seen this before, haven't we? And so what would happen here is you would have a cost function and you would have a revenue function, okay? And then you could, well, we'll see this. One way to actually solve a system is by graphing each of those two linear equations. And so if you graph your cost function, okay, it'll be this line. If you graph your revenue function, it'll be this line. And wherever they cross, that's where the solution is. Okay. And so here you could see that, you know, whatever we're talking about, we need to sell 7 to be able to make 33. This says hundreds of dollars, so that would be like $3,300. Okay, and this point at which those two functions cross, this point that would solve that system of equations, this is the break-even point. Okay, and so you can see for values of x, or for numbers of units that exceed 7, you're going to make a profit. And selling less than 7 units, you're actually going to be in the negative. Your revenue is actually not going to reach the cost. Okay, so that's an example. Now I know we were able to solve something like this. We could have done it in section 2.4 just by simply subtracting from the revenue function the cost function and setting it equal to 0. That would be another way, but let's see what else. There's some good examples in here.
Take care. Yeah, fine to meet you.
Well, here this said, well, I'm not too fond of that example. Oh, this is a good one. It says here, Jamal is choosing between 2 truck rentals. Hey, Jim. Alright, sorry about that, guys. Yes, it says Jamal is choosing between 2 truck rental companies. And this would be a very interesting real-world problem. Okay, it says the first, Keep On Trucking Incorporated, charges an upfront fee of $20 and 59 cents a mile. And then the second, Move It Your Way, charges an upfront fee of $16 and then 63 cents a mile. And so the question is, when will Keep On Trucking be the better choice for Jamal? And so again, really what you're doing is you would set up 2 linear equations that model the cost of renting a truck from each of these 2 different companies, and you could set them equal to each other, or you can set them up as a system of linear equations. You can solve it, and that solution will be the number of miles for which the 2 companies cost the same. And then if you exceed that number of miles, one company is going to end up being cheaper than the other company. But if you don't exceed that number of miles, the other company will actually be cheaper. Okay, so that would be a good problem. And then here's another one. I saw down here, yeah. It says a chemist has 70 milliliters of a 50% methane solution. How much of an 80% solution must she add so that the final solution ends up being 60% methane? Okay, so this is another good real-life example in which you could employ a system of linear equations and figure this out. Okay, and then lastly, look at this one. It says a river cruise ship sailed 60 miles downstream for 4 hours. Okay, so it's sailing, this could be downstream, I guess. And then it took 5 hours sailing upstream to return to the dock. Okay, so it was sailing at 60 miles an hour. That's what the throttle was set at. Or, well, no, it doesn't say. It just sailed 60 miles downstream, and it took it 4 hours. But then it took it 5 hours to get back upstream. And so what you could do is figure out the actual speed of the ship relative to the water. Okay, the water is actually moving. That's why it took it less time to sail downstream than it did to come upstream. So the water is moving, but with respect to the water, we could figure out how fast is the ship actually sailing. Okay, so those are some examples. And then I put a couple in here in your notes. This is an interesting one here. It says Teddy invested $5,000, part at 11% annual interest. And we'll talk more about this later on in the course. And the rest at 13% annual interest. Okay, which that's actually a pretty good interest rate, guys, if you're an investor. So he's got $5,000. He invests part of it at 11%, and then the other part at 13%. But he forgot how much he invested in each account. So, but he does know that he receives $610 interest total at the end of 1 year. And so the question is, well, how much did he invest in each of those accounts if this was the total amount that he made in interest? And so having a system of linear equations, we could solve this. And then one last one here. This one's similar to the solution problem earlier. It says how much cream that is 20% butterfat should be mixed with milk that is 5% butterfat To get 10 gallons of cream, that's 14% butter fat. Okay, so this is another example in which a system of linear equations would allow us to figure that out. Okay. All right, so you've probably gathered by now a system is going to look like this. Now in this section, the system will be given to us, and we'll just be asked to solve it. But in later sections, specifically 3.6, well, in the next section, we'll actually have to come up with a system ourselves. So they'll just give us a word problem like this. We'll have to construct the system and then solve it. And so sometimes that might require moving some terms around. So in our system, we want to make sure all of our variable terms are on the left-hand side, and then all of our constant terms are on the right-hand side. And once we've done that, we can proceed to solve it. Okay. And then furthermore, if it's a system of two equations and two variables, our solutions will be of this form. There'll be a value for x and a value for y. And then if it's a system of three equations and three variables, we'll have what's called not an ordered pair, but an ordered triple, okay, in which we'll have a unique value for x, y, and z. And guys, I will point out that sometimes it's impossible to solve a system. There won't be any solutions. And then sometimes there will be infinitely many solutions. Or in other words, one equation is really just a copy of the other equation, even though they look different. It's actually the same equation repeated. Anyway, I can't remember if we'll see any of those or not. All right, so we're going to start with a system of two equations and two variables. Okay. All right, so the first thing, we're going to use what's called the elimination method to do this. And I'll illustrate this here below here in a minute. So first, number one, we want to write both equations in this form. Okay. This just means get all your variable terms on one side if they're not already. I think most of your problems, the variable terms are going to be on the same side. And then you would try to clear any decimals or fractions if you had any. But I don't think that we're going to see any. Then you choose a variable to eliminate. And it doesn't matter which variable you choose to eliminate. Alright, and then if you look at number 4, it says make the chosen variable's terms opposites. Okay. By multiplying one or both equations by appropriate numbers if necessary. Step 5, eliminate a variable by adding the respective sides of the equations and then solve for the remaining variable. And then you have to do back substitution to figure out what that other second variable is. Alright, so that probably didn't make any sense, but it will once I start illustrating this. So let's look at example 1 here. Alright, so example 1, this is our system. Okay. We've got our x and y's on the left-hand side. We've got them vertically aligned. They've got to be vertically aligned, guys. And so you just pick a variable to arbitrarily choose to eliminate. So I can try to eliminate my x's first and my y's first. But I'm going to try to eliminate my y's first, and I'm going to show you why. Because in the process of elimination, it requires that we vertically add each of these columns or each of these terms. Okay, that's how we're going to do this. And I can see, looking at my two y terms, that they are opposites of each other. One is negative 3y and the other one is positive 3y. And so if I go about adding each of these columns, these two y terms will be eliminated because they're additive inverses, or they're opposites. And so that's where the name comes from. The elimination method comes from. So guys, when you're first starting out, just inspect and see if you have a couple terms that are already opposites, because if you do, go ahead and go with those. That'll save you a step or two. Alright, so I'm going to go ahead and start adding each of these columns. So, my x column, I've got 2x plus a negative 4x. That would give me a negative, whoops, did not add those correctly. That would give me a negative 2x. But then when I go to add my y column, a negative 3y plus 3y is 0. Okay, and so the y's are eliminated. And you're going to bring down your equal sign and then add your two constants. 0 plus negative 1 is negative 1. Okay. And so guys, once you eliminate one of those terms, you have an equation in one variable. And we can solve this one. Okay, you would solve this one by dividing both sides by negative 2. Because the x is getting multiplied by negative 2. So we do the opposite. On the left-hand side, negative 2 divided by negative 2 leaves us with 1x equals, and then on the right-hand side, we're just going to be left with a fraction. The two negatives, however, will turn into a positive, so we're going to end up with 1/2. Okay. And guys, do not be alarmed if you come up with a fraction value. I think most of these, your solutions are not going to be fractional, but there could be one or two. Alright, so we know the value of x. We've partly solved this system. The value of x is going to be 1/2. Okay. Now we need to figure out the value of y. Well, once you know the value of x, you can simply substitute that value in for x in either of these two equations, and then solve it for y. Okay? And so I'm just going to choose my top equation. So I'm going to rewrite it. And I'm going to substitute. This is what I refer to as back substitution. Or just substitution. I'm going to take that 1/2 and I'm going to plug it in for that x. So I'll have 2 times 1/2 minus 3y is equal to 0. And so right here, you can do this in your calculator if you need to. Or you can just think about these 2's dividing out, leaving you with 1. And in any case, 2 times 1/2 is 1. And so we'll have 1 minus 3y is equal to 0. And so now you can see we're just going to go ahead and solve this one for y. So I'm going to subtract 1 from both sides of the equation. We'll have 1 minus 1, that's 0. And we'll be left with negative 3y is equal to negative 1. And then, again, we're going to divide both sides by negative 3. And we'll end up with y is equal to, again, this is going to stay a fraction, and it's going to become a positive 1/3. Okay? And so that'll be our value for y. And so this right here, this ordered pair, this is the solution to this system right here. It's only these values for x and y that'll make both of these equations true, or in other words, solve that system. See guys, that's how a system of equation works. Typically, one variable will represent something, the other variable will represent something else. You'll be able to come up with two equations, and then you'll set those equations to different numbers depending on what the conditions of the scenario are. Okay, and like I said, we'll see some actual examples in the next section. Let's see. Well, I was actually going to set one of these up for you just to kind of show you that process real quick, but I guess we'll wait until 3.6. Okay, because the important thing now is that you know how to solve the system. And we can look at some examples, more examples in 3.6. All right, example 2 here. Let's see. Okay. Example 2, it says solve this following system. Okay, so again, it's a system of 2 equations and 2 variables. And I've got my variables on the left. They're vertically aligned. Okay. But I'm going to inspect this one and see that if when I add these, if any of my variable terms will cancel, and the answer is no. Okay. And so I need to choose which variable I want to work on trying to eliminate. Okay, guys, I'm going to go with y again. You'll see why here in a minute. All right. So if I just go ahead and add these, nothing gets eliminated. Okay. However, looking at my y's, I do notice that this 6y down here is a multiple of the 3y on top. So if I were to multiply the top equation by a number, and I'm going to say -2, you'll see why here in a minute, then if I distribute this -2 to that top equation, that equation doesn't change. It changes the way it looks, but it's really the same equation because I would be multiplying both sides of it by -2. Okay, so it's going to stay balanced. All right, now why did I choose -2? Well, because if I multiply this term 3y by -2, that'll turn it into a -6y. And then it will cancel with the positive 6y that I have below it. Okay, it'll turn my two y terms into opposites. So that's what we're trying to do here. That's why I didn't go with the x's, because there's not a nice number that I could turn. You see, I've got a 3x on top and 2x on bottom. I would need a fraction to turn the 2x on bottom into a -3x. And I didn't want to have to bother with using a fraction. Alright, so what I'll do, first thing, is I will multiply that entire top equation by -2. And that'll give me a new equation. Okay, so -2 times 3x, let's see. Let's write this over here, will give me -6x. -2 times 3y will give me -6y equals, and I'm going to need to kind of partition this because I wrote a little bit too far down. And then finally, -2 times 15 is -30. And don't forget to multiply your constant by that number as well. Sometimes students will forget that. And then I don't need to manipulate my second equation, so I'm just going to rewrite it below my first one. And now, guys, you can see that when I go to add these columns, my y's will eliminate, right? Because they're opposites of each other. So I can go ahead and cross those out. Now I need to add my other columns. -6x plus 2x will be a -4x. Bring down my equal sign. And then over here, a -30 plus 22 will be a -8. And then we can divide both sides by -4. And so we're going to end up with x is equal to, this will be a nice 2. Okay. And so that you'll find that this process is very repetitive. Okay. So now that we know the value for x, and I could go ahead and write that in over here. Now I need to find my value of y. Okay, so I'll do the substitution again. And guys, just for the sake of consistency, I will choose to substitute 2 back into my very top original equation. Although technically it doesn't matter which equation you use. Okay, so I will say rewrite my original top equation, 3x plus 3y is equal to 15. And we'll take that 2 that I found and we'll plug it in for that x. So I'd have 3 times 2 plus 3y is equal to 15. Well, we know 3 times 2 is 6. Okay. And then I just keep going, guys. I subtract 6 from both sides of the equation. So my 6's are gone. That leaves me with 3y is equal to 15 minus 6 is 9. And then finally, if I divide both sides by 3, I'm going to get that y is equal to 3. Okay, so that is my corresponding y value. So x has to be 2 and y has to be 3. So that is my solution. Okay. Alright, I can't ask you guys if you have any questions. I guess I could rhetorically, but... Alright, well let's look at one more before we go to the part 2 video. Alright, this last system here, I should have really given myself a little bit more room. Alright, so I'm looking at this system, and I can see my x's and my y's are already aligned. However, nothing's going to cancel as is. So then I go about looking at my x's and y's and seeing if one number is a multiple of another, because that's what I did up here. I saw that 6 was a multiple of 3, so I knew I could easily turn this 3 into a negative 6. But looking down here, guys, 7 is not a multiple of 3. And furthermore, 5 is not a multiple of 2. Okay. So then what do? Well, I could technically choose to multiply one of these equations by a fraction. To say turn this 3 into a negative 7, I could do that with a fraction, but I'm going to try to stay away from fractions. What's going to happen here is we're going to have to multiply both of these equations by 2 different numbers. But that'll keep us from having to use fractions. So you just decide on a variable that you want to eliminate. For this one, I'm going to choose x, okay, just to be a little different. So I'm going to multiply my top equation by 5. So basically, you're looking at the other coefficient of x. Okay, so I'll multiply my top one by 5, and I'll multiply my bottom one by not just by 2. I'm still going to be using the other coefficient of x, which is 2, but I'm going to let it be a negative 2. Why am I making it a negative? Well, because when I actually am finished here, I want one of the terms to be positive and one to be negative. They've got to have opposite signs or they're not going to eliminate. And you can see that by doing this, we're going to end up getting a 10 and a negative 10. Okay, so by always using the opposite coefficient and maybe changing its sign if necessary, then you're going to end up with coefficients of x that are opposites. Okay, so let's go ahead and do this. Alright, so we'll distribute the 5 to the top equation. 5 times 2x will give us 10x. 5 times 3y will give us 15y. And then 5 times 17, I believe, will give us 85. And then I'm going to distribute my negative 2 to my second equation. Negative 2 times 5x is negative 10x. Negative 2 times 7y is a negative 14y. And then negative 2 times 29 is 58. Okay, so now I'm ready to eliminate. Okay, and so you can see my x's are going to turn into 0 because one's a positive and one's a negative. And then we get a little bit lucky here, guys, because 15y plus a negative 14y is just a 1y. Oh, I forgot to make this a negative 58. You gotta be careful on these. And you'll see in the part 2 video, 1, small mistake can derail your entire problem. All right, 85 plus a negative 58, I believe, will be 27. Okay, so that is going to be my value of y. So y is 27. Now we need to find the corresponding value of x. So we'll do our substitution again. So again, to be consistent, I'm just going to reuse my top original equation. Okay, so it's 2x plus 3y is equal to 17. And I'm going to take that 27 and we'll plug it into that y. So I have 2x plus 3 times 27 is equal to 17. Well, 3 times 27 is 81. 2x plus 81 is equal to 17. Now I'm going to need to subtract 81 from both sides. And that'll leave me with 2x is equal to, I believe that's going to be negative 64. And then I'll divide both sides by 2. And this will give me x is equal to negative 64 divided by 2 is a negative 32. Okay, and so that's the value for x that I come up with. So you can see in each of these three problems, the procedure is basically the same. It's just getting started. It could be a little different. Sometimes, like in example 1, you might not have to manipulate either equation. And then, like for example, in example 2, you might just need to manipulate one equation. And then in example 3, you're going to have to manipulate both equations. Okay. So there's one of each there for you. An example of each. Okay. For you to refer to whenever you're working on your homework. Alright guys, well I think I'm going to stop the part 1, and in part 2 we're going to look at systems of 3 equations, 3 variables, okay? And I might even have to make a part 2, we'll see I guess. Because these take a lot more, require more work, because you've got more going on, you've got a third variable. You can see I allotted more room in solving these as well. Alright, well I'll see you in part 2.